Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for week number 9 for our course of communication systems. In our today's discussion, we will be talking about random processes. Mathematically, we name it random processes, but from our engineering point of view, we'll call them random signals. So, what is a random process? Random process is actually another version of random variable. As we recall, random variable generates a number corresponding to outcome of a random experiment. However, random process, it generates a function of time in result of an outcome of a random experiment. So basically, a random process maps experimental outcome into real functions of time. So that means a random process is actually function of two things. One is the random variable and another is time. So basically, random process depends on these two things. So any function of time is named as sample function, and the collection of sample functions is named as ensemble in case of random processes. So here's the graphical illustration regarding a random process. Let us take a simple case where there are multiple resistance and we are trying to measure the noise voltage across those resistances. So there are number of resistances which are shown here. If we measure the voltage across first resistor, so we will be getting a function of time with respect to time, which is called a sample function. If we measure another voltage across another resistance, so you can see that it will be generating another waveform for the voltage, which is another sample function, and so on. For all resistances, we will be getting a number of waveforms. And if we observe all those resistances at a certain amount of time, so we will be getting random values here, here, and here, and that means these are actually different random variables which corresponds to a specific time here. So if we observe the time signal at time t1, so we will be getting a value of random variable v1. If we observe at another time t2, we will be getting another random variable which is v2, and so on. So you can see that this entire random process is actually dependent on random variables, because each observation will give certain random variable, plus it's dependent on time as well, because each observation has some dependence on time as well. So this collection is generally called ensemble. As we previously discussed in case of random variables, that we are more interested in calculating statistics of the random phenomena. So for the case of random processes, because there are two types of dependencies, so we can calculate statistical average from two different perspectives. What are those two different perspectives? First, we will calculate the average with respect to time. So that is called a time average, which is denoted by this bracket here in our textbook. So we can calculate the average with respect to time, or we can calculate average with respect to random variable. So we can also calculate as we have done it before. So we can calculate averages with respect to random variable, which is generally named as ensemble averages, which can be calculated through this expectation operator as we previously discussed. So we know that how we can calculate the averages related to different random variables as well as the random processes. As you can see that if you want to find mean value of this random process vt, so we can calculate it by taking expectation of this vt, which however, now you should notice that this v is not a constant number, because it's dependent on time as well. So the average value or mean value that you will be getting in general, that can be a function of time. And secondly, if you can see that if we observe at different time t1, so you will be getting mean value of that random variable, but at different times you will be getting different random variables. So at time t1 you will be getting a different mean value for random variable which is v1. At time t2 you may be getting a different average value at time v2, and so on. As we notice that this random process is actually a function of time, therefore we have to investigate the relationship at two times as well. So for this relationship we calculate autocorrelation function. As we know that correlation is actually the matching process which shows that how signals are closely related to each other. So we are calculating the correlation of the signal V at time t1 and t2. So at two time intervals we are calculating the correlation or matching of the signals. This correlation is mathematically defined as the expected value of the product of two samples, that is whatever voltage sample you have at t1 and t2. So this is the correlation at two different time instances. Here you should also note that if these two samples they are uncorrelated, in that case the correlation function which will be equal to the product of individual averages, as we have previously discussed in the case of independent random variables as well. Another important thing that you should notice that if we set t2 and t2 to be equal, t1 and t2 to be equal, that is t2 is equal to t1 is equal to t, in that case this autocorrelation function, it can be written as rv t into t, which is actually expected value of v square, which is actually the mean square value. So from autocorrelation function we can also calculate mean square value as a function of time by simply setting t1 and t2 equal. Another perspective related to random variable is their stationarity. What are stationary random processes? Actually, for stationary random processes we actually take two different perspectives. Either we call it strict sense stationary or wide sense stationary. So a process is actually said to have is said strict sense stationary if all statistical properties of the process are independent of time. So no matter what statistical parameter you calculate, the parameter comes out to be independent of time. In that case we say that the random process is strict sense stationary or SSS. However, for most cases we are actually interested in these two parameters, mean and autocorrelation function. So we define another type of stationarity which is called wide sense stationary. A process is said to be wide sense stationary if its mean is constant. So mean comes out to be constant, and autocorrelation is function of time difference only, that is t1 minus t2. So it is function of difference only. So a process is said to be wide sense stationary if mean comes out to be a constant number, it's not a function of time. And autocorrelation is function of time delay, that is time difference only. So typically we write it as tau, where tau represents the time delay. And you can see that if we substitute tau equal to 0, in that case this autocorrelation function at 0 will give you the mean square value as we previously observed as well. So in most cases, for our point of view, we are interested in checking this process because most of the processes that we deal with, they are actually wide sense stationary. So we generally focus on this property, that we need to calculate their mean and autocorrelation to check the stationarity of the processes. In order to understand these different types of calculations related to random processes, let us take a very simple problem related to the random process. So consider an oscillator set at some non-random amplitude A. So A is not random, so it's a constant number, and a frequency omega naught. Omega naught is also deterministic, it's not random. But the phase is random. So we are given the condition that the phase is random. So the ensemble of the sinusoids constitute a random process defined by this relationship. So this relationship defines the random process. Vt is equal to a cos omega naught t plus phi, where phi is the random variable, a and omega naught are constant, where phi is random angle. And this random variable is defined to be uniformly distributed over 2 pi radians. So this one follows uniform distribution, as we discussed in our last lecture as well. So it follows uniform distribution. So before going further, let me mention what is the probability density function for this random variable. So because it follows uniform distribution, so you can use the formula of uniform distribution, and it is spanned over the range of 2 pi radians. So it exists between 0 to 2 pi, and the PDF is 1 upon 2 pi. So PDF for uniform distribution, it is given as 1 upon beta minus alpha. So 1 upon 2 pi minus 0 is 1 upon 2 pi. So this shows the PDF of the random variable, which is phase angle in this case. Okay, so now that we know that phi is random angle in this situation, which has uniform distribution, using this information we want to find the mean value of the process, which is expected value of Vt. We want to find autocorrelation function defined by Rv t1 t2. We will find the mean square value, expected value of V square t. We will find the time average as well. So you can see that the first three samples A, B and C, they are actually ensemble averages, because they are asking you to find the averages with respect to the random variable, whereas this D is time average and E is also time average, but it's V square t, average of the square. And last thing, we also want to comment on the stationarity of the process, so we'll discuss it after we have done the calculation. So let us start our solution. So first part is to calculate mean. So mean is given as expected value of Vt, and by definition we know that the expectation is calculated by multiplying the function with the PDF and integrating it over the desired range, the range where the random variable exists. So for our case, this distribution is given as 1 upon 2 pi in this range of 0 to 2 pi. So our random variable exists in this range from 0 to 2 pi, and we have this PDF which is substituted here. And you can see that 1 upon 2 pi and a, these are constants, so I have taken them out of the integral. So a upon 2 pi is can be written separately, and we have to integrate this function 0 to 2 pi cos omega naught t plus phi d phi. Cosine function is a very simple function. You can easily calculate its integral. Integral of cosine function is sine function, and then you can substitute the limit. So you would see that that result comes out to be 0, because we know that the cosine function is actually a symmetrical function about it has a positive half cycle and a negative half cycle, and whenever we have to integrate this cosine function over a entire period of the function, which is 2 pi, so it is being integrated over the entire period, so we have to encounter a positive half cycle and negative half cycle. Eventually that integration would come out to be 0. So without going into mathematical detail, I have directly substituted this integral to be equal to 0. If you want, you can simply substitute you simply integrate and substitute the limits in order to get this answer. And from here we can see that this mean value comes out to be 0. Okay, Now move on to the second part, which is calculating the autocorrelation function for the given question. So autocorrelation function RVT1 T2, it is defined as expected value of VT1 VT2. This is the basic definition, and we know that how we calculate expectation. Whatever function is given VT1 and VT2, we have to multiply it by the PDF, and then we have to integrate over the entire values of the random variable. For our case, our random variable exists from 0 to 2 pi, so therefore we have to integrate in this range from 0 to 2 pi, where this PDF has the value 1 upon 2 pi. So I have substituted the value of T1 and VT2, which is actually here we should have A here. A cos omega naught T2 plus phi. So there are two values here. This A and 1 upon 2 pi, these are constant. A square upon 2 pi is constant. I have taken them out, and we are left with these two functions which are being multiplied, which are the values at T1 and T2. In order to integrate this function, we have to use product to sum formula. You can see that this is the in product form, and if we use a product to sum formula, so you would see that this angle, one time they will appear as sum, and for other time they will appear at difference. So from difference you can see that this phi and minus phi, they will go off, so eventually you will end up with cos omega naught t plus minus omega naught t2 d phi. And for the first term you will see that cos omega naught t1 plus omega naught t2 plus 2 phi, and we are integrating it with respect to phi. So I have separated the integral for both the terms here, so we are writing them separately. So if we consider this first term here only, you can see that this is being integrated with phi to phi, and this is a simple cosine function here. It's a simple cosine function, and this is being integrated over this entire period 0 to 2 pi. In fact, this is being integrated over two periods, because we do not have phi here, we actually have 2 phi here, so it is being integrated over two periods. However, if the result for single period is 0, so eventually the result for two integration over two periods will also be 0. So the integral of first term will be 0 definitely. So so we can take this term to be 0. So we will left with the second term, and from second term you can see that cos omega naught t1 minus t2, it can be written as cos omega naught t1 minus t2 d phi. But if you notice that this integration is being performed with respect to phi, and for this function we do not have phi in this function, so it will be treated as constant for this integral. So cos omega naught t1 minus t2, it can be taken out of the integral. So if we take it out from the integral, so we will left with this d phi only. So if we integrate d phi, it will give you result phi with a limit from 0 to 2 pi. So if we substitute the limits in this expression, so this comes out to be 2 pi here, a square upon 4 pi cos omega naught t1 minus t2 into 2 pi, and this 2 pi can cancel out with this 4. For simplicity, as I mentioned earlier, that we can write t1 minus t2 as tau, which is time delay. So I have substituted t1 minus t2 as tau, so I can write it as a square upon 2 cos omega naught tau, so this autocorrelation function is dependent on this time difference tau, which is illustrated here. Let us move on to the third part, which is calculating the mean square value E of v square t. Although we know that we can calculate this second moment E of v square t by integrating the function, but as we have previously calculated the autocorrelation function, it is much easier to calculate this v square t from autocorrelation function. How can we do that? We have to simply substitute this t1 and t2 to be equal. So if t1 and t2 are equal, in that case this autocorrelation function actually represents expected value of v square t. So in order to calculate the mean square value, expected value of v square t, so we substitute t1 is equal to t. Alternatively, we substitute tau equal to 0 because t1 minus t2 is tau. So tau equal to 0, substituting tau equal to 0 gives you the expected value of v square t, that is the mean square value. So if we substitute it here, you can see that tau is replaced as 0, so cos 0 is 1, therefore expected value of v square t comes out to be a square by 2. Now let us try to solve the time averages. So first we start solution of Vt, time average of Vt. You should notice that in general the time averages, they are written like this, that Vt is actually limit t goes to 0 from minus t by 2 to t by 2 Vt dt. So this is the generalized form. However, we do not need to use this form in this question because the function that we are dealing with is a periodic function. So we can calculate the integral by solving the function over a single period. So that is the time period which is represented as t naught here. So for time average of Vt, we have to integrate this Vt over this entire period from 0 to t naught and divide it by the overall period, which is 1 upon t naught. If you substitute the values here, Vt is equal to a cos omega naught t plus phi dt, and 1 upon t is at the output. 1 upon t naught is actually being multiplied to give the average value. You should also note that this is the time average, so we are performing integration with respect to time, not phi. For this particular case, phi should be treated as constant because this is the integration with respect to time, not phi. So if we integrate it, in that case if we integrate it, you would see that the result comes out to be sin omega naught t plus phi 0 to t naught. I have forgotten to mention omega naught at the denominator. I'm sorry for that. I will correct it in the final version. So a upon t naught sin omega naught t plus phi 0 to t naught, this is the integral, and if we substitute the values here, so it will be given you sin omega naught t plus phi minus sin omega naught t naught plus phi minus sin 0 plus phi. You can see that omega naught t naught can be written as omega naught is 2 pi f naught, where t naught is 1 over f naught. So this f naught goes off, so eventually omega naught t naught is actually 2 pi. So this omega naught t naught can be written as 2 pi plus phi, and the second term is sin phi only. And sin 2 pi plus phi, we know that sin is periodic with period of 2 pi. So therefore this sin 2 pi plus phi, theta can be written as sin theta. So this sin 2 pi plus phi can be written as sin phi minus sin phi. So eventually, because both terms are same and being subtracted, so they will cancel out. So you will get the average value to be equal to 0. So now let us move on to the E part, which is calculating the average value of v square t. It should be calculated in same way as we calculated the time average for Vt. So we are multiplying it by 1 upon t naught for averaging purposes, and we will integrate v square t from 0 to t naught because we are calculating the average value of v square t. So if we simplify this, a cos omega naught t plus phi whole squared, so a square is a constant, so I can take it out from integral. Cos square omega naught t plus phi can be integrated by using a mathematical relationship given here, which is cos square theta is equal to 1 plus cos 2 theta upon 2. So this is 1 plus cos 2 omega naught t plus phi upon 2 dt. This 2 is a constant number, so I can write it before the integral. So a square by 2 t naught is here. You can see that there are two terms. One is the first term is 1, so this integral can be written as 0 to t naught dt, and second term is this cosine function, which is 0 to t naught cos 2 omega naught t plus phi. You can see that the second function is integral of this cosine function over this entire period of the cosine function. So eventually this integral will give you a 0 result. You can try it by solving it as well, but of course this will give you 0. So I can ignore this integral. So first integral is important here, 0 to t naught dt, and we have the product term a square upon 2 t naught. So if we simplify, if we integrate, so dt will be integrated to t, so t with the limit 0 to t naught, and if we substitute the limit, this will be t naught minus 0, and of course this t naught will cancel out by this t naught, so this v square t comes out to be a square by 2. So this is the time average of v square t. And now if we talk about the last part, which is regarding commenting on the stationarity, you can see that the mean value came out to be a constant number mv was calculated in the first part, that is 0, and autocorrelation came out to be function of t1 minus t2 or time delay tau only. So you can see that the autocorrelation is function of this t1 minus t2 or tau, and these two are the properties that we need to identify for the wide sense stationary process. So this random process which was given in the problem, it actually satisfies both the properties of a wide sense stationary process. So we can conclude that this random process is actually a wide sense stationary process. At this stage, I want to mention another important thing, is that we have calculated the values here. You can see that the time average which is given, the ensemble average which is given here is actually equal to the time average. You can see that the mean value that we calculated here and the time average that we calculated in part D, both are 0. Similarly, time square, mean square value, that comes out to be a square by 2, and the time average of v square t also come out to be a square by 2. So there are certain processes in which the ensemble averages, they come out to be equal to the time averages. So these types of random processes, they are called exodic processes. So this one is also an example of exodic process, because the time averages, they are equal to their respective ensemble averages. So this was a simple problem illustrating how we can calculate the time average and ensemble averages in case of a random process. However, that was a purely mathematical description. I want to shed light on some physical quantities associated with the random process, because we are dealing with signals. The word random process is actually a random signal. So signals, they have some physical interpretation that we use to analyze in physical systems. So random process has some the different statistics of the random process, they have some significance from the perspective of physical parameters. So if we try to identify those physical quantities which are illustrated by the random process, you should notice that this expected value is actually this mean value of the signal, which is mean value, and this is mean square value, which is actually defined by this relationship sigma v square plus mv. Sigma v square is the variance and mean square value. If you look at this mean value, so mean value is actually representing the time average, or which is actually from practical perspective is a DC component in the signal. We know that different signals, they have DC and AC components. So this signal has a DC component which is equal to the mean value of the signal. So mean value represents a DC component. Similarly, if we square the mean square value, and that means if we calculate the square of this time average of the square value, mean value, square of the mean value, this is actually mean value squared. This one is different than this one, because you can see that these two are different, because this one is mean value squared, this one is squaring and then calculating the mean value. Okay, so now let us come back to this mean squared value. So if we square the mean value, that means we are squaring the DC component. That means we will be calculating DC power in the signal. Similarly, if we calculate mean square value, so this is actually average value of V square for the entire signal. So it gives you a total average power. So it is actually average power. V square is actually representing power, and we are averaging. So this gives you total average power in the signal. You can see from here, this is total power V square T, this is the DC power, and of course you can easily see that this sigma square V is actually AC power. So this variance sigma V square, it gives you total AC power in the signal. So whatever power is there in time varying components, that is represented by variance of the random process. Similarly, if we calculate the standard deviation, which is actually square root of this variance, so that will give you RMS value or root mean square value of the AC component of the signal. If you recall, at initial stage I also mentioned that the power in noise is illustrated by its variance. So you can see it from here, because in case of noise the DC component is 0, it has mean value equal to 0, so the total power is equal to the AC power, which is the variance of the noise. So for the case of noise, this variance also represent the power in the noise component. So far we have talked about the parameters, mean and autocorrelation function. So if we discuss the autocorrelation function for WSS processes, we have noticed that the autocorrelation function can be represented in terms of time delay, which is difference between two times t1 and t2. So this autocorrelation function is mathematically written as this formula. RV of tau is actually expected value of Vt multiplied by Vt minus tau. This is the delayed version of the same signal, or alternatively we can write it like this. So you can see that we are calculating correlation of the signal with the delayed version of the same signal. This autocorrelation function has certain properties which are illustrated here. You can see that the first property is that the signal is symmetric. The autocorrelation function is symmetric. So whatever behavior you see for minus tau, negative values of tau, you would see the same behavior for positive values of tau. Similarly, we can calculate power from the autocorrelation function, power which is given as the mean square value, and this mean square value is actually calculated when we have tau equal to 0. So the value of the autocorrelation function at tau equal to 0 gives you power in the signal. Third property is that the maximum value occurs at tau equal to 0. Other values can be equal or less than whatever value you have 0, but those cannot be greater than what you have at tau equal to 0. So there will be no value which will be greater than what you have at tau equal to 0. Another important parameter related to random processes is known as power spectral density. So what is power spectral density? Power spectral density is actually Fourier transform of autocorrelation function of the random process. So if you calculate the Fourier transform, so that Fourier transform is called power spectral density. What is this power spectral density? Practically, this PSD represent distribution of signal power in frequency domain. So it is distribution, or in other words, is signal power per unit bandwidth. It's measured in watts per hertz. It is not power, it is related to power. In order to calculate the power, you have to integrate this PSD over the entire frequency range, that is from -infinity to +infinity. But since we know that the signal spectrum at positive and negative side, they are symmetrical, so therefore we can use a simplified version of this integral, that we can calculate it in the positive side only, 0 to infinity, and multiply it by 2 by virtue of the symmetry that is present in that signal. So similarly, if you want to find power in a specific frequency band from f1 to f2, we can calculate this power by simply integrating this power spectral density in the required band, which is from f1 to f2. So this power spectral density actually, as I mentioned, it's a distribution of power. So for any real valued signal xt, the power spectral density has certain properties which are listed here. Number one, this power spectral density is always a real function. So there, it will not be a imaginary function. It should be a real function. Second, the power spectral density is always greater than or equal to 0. So it is a non-negative value. It cannot take any negative value in any case, because it's related to power, so it does not take any negative value. The third property is same, that the power spectral density is symmetric about the frequency origin. So whatever behavior you see at positive frequencies, you would see the exact replica at negative frequencies. The fourth thing that I have previously mentioned as well, the power spectral density and autocorrelation function, they form a Fourier transform pair. So time domain representation is autocorrelation function, whereas the frequency domain representation is the power spectral density. And total power can be calculated from this autocorrelation function or from the power spectral density. In order to calculate the power from autocorrelation function, you have to substitute tau equal to 0. And for calculating the power from the power spectral density, you have to integrate this power spectral density in the range from the entire frequency range, whatever you are interested. So this was the brief discussion related to the random processes. I tried to identify some of the important parameters, which are mean, autocorrelation, and power spectral density, that are commonly used to describe a random process. So we stop our discussion here. Inshallah, we will be starting discussion on noise in our next lecture. Thank you all.